Hello, everyone. Hope you're doing well. Let's talk about, and backing up a little bit here, the types of spaces that we have been working with so far. In the first couple of weeks, we were working specifically in the space Rn. We were looking at a space with a good bit of structure on it. You can add and subtract. You can compare in the one-dimensional case, whether numbers are greater or less than. You have a lot of structure on your space, which allows us to make a lot of theorems. We've talked about how some of those theorems translate nicely into the types of spaces we've been looking at for the past few weeks, like the metric spaces we've been looking at. In particular, the functional metric space is what we've just been discussing from these past couple of weeks. These metric spaces, which consist of functions on some other sort of space. And we've seen lots of interesting and unique theorems come out of our study from that direction. And what we've gone through so far are some of the kind of beginning building blocks for anybody who wants to go off and do something in those spaces. Whenever we think of somebody going off and doing something in functional analysis, for example, we think that we would be a little bit ill-equipped if we didn't have the hammer of Stone Weierstrass and the pickaxe of Arzela Ascoli ready to go into that place of study. So we're going through all of these different types of metric spaces, but notice with the transition from metric to functional metric spaces, we didn't actually change any of the structure on this space. We just said what the different elements of the spaces are. Today, we're going to introduce a type of metric space that introduces a little bit more structure to our space. The picture that we've been looking at so far for the spaces of our in question have been spaces in which we can form open balls. Essentially, you would be able to say, I can take a point and I can consider points that are close enough to it, right? And utilizing this notion of a metric here. So there was a way to define open balls in this place. This is kind of the way of being able to measure distance as well in between 2 points. So even though we don't actually end up drawing these, because oftentimes these lines don't end up looking like lines in metric spaces, there is some sort of way to form, say, what we might call a geodesic. A geodesic means a line segment that measures the shortest distance between any 2 points, and the length of that would be the distance between points X and Y. So the length of that line would have that sort of distance. So we've been able to form this notion of what is called kind of a geodesic. We've been able to figure out, okay, what is the length of the shortest line segment? Now, I may not be able to graph it for you on this paper, but given kind of how we go through and write this paper, you can imagine that there does exist some sort of segment that connects us from one point to another, and I can tell you what that length is. It's just the distance between those 2 points. A normed vector space allows us to do something a little bit more. It allows us to add in a little bit of structure past this point. In particular, we're going to add in the structure of a vector space here. Now, you may recall that a vector space has particular axioms that go with it. Many of those of which are important in this structure are things like zero. There exists a zero vector in a vector space. And in particular, this zero has to act like a zero in the sense that when you add this vector to any other vector, you get the same one. That means that addition needs to exist inside of this space. What's more, you can also take a vector and you can multiply it times 2 or times 3. Note, you may not be able to multiply the vectors themselves, but you do get scalar multiplication. A multiplication by just a numerical amount on each of the vectors. There exists zero, addition, scalar multiplication, some of these things. I'm not going to go through and list the entire idea here, but the idea is that many of these operations satisfy the types of properties that you would hope for. There is commutativity, there is distributive property with respect to the scalars. There's also the fact that whenever you multiply a vector times the scalar 1, then you get back the vector itself. So you get many of the conditions of these types of forms that work well with these two new operations. In particular, addition and scalar multiplication. But we're also going to add in a little bit more structure to the vector spaces. Without this extra structure, the vector space is an algebraic object. And let me specify what I mean by that. An algebraic object means that it works in terms of its algebraic operations. The operations that are you can add and you can scalar multiply. Now, a lot of this stuff can sometimes be put in air quotes because there aren't really official things that make something completely algebraic or completely analytic, as I will claim the normed vector space is, at least in terms of our heuristic here, how we think through these problems. Adding a norm on a vector space makes it an analytic object. We are extending beyond just the algebraic operations of plug in two numbers and get out another number. We're going to add an object to it that makes it more analytic, that gives it some sort of notion of a continuous variation with regards to what happens when you plug in these numbers. So we'll discuss a little bit more about what that looks like. In particular, you might recognize the norm when I give an example here, because we do have a norm on the real numbers, and it is just the absolute value function. The real numbers has the norm of an absolute value, which just when you plug in a real number, you measure in particular basically it's kind of how it would work in terms of distance. We can kind of think of this in terms of the metric. How far is the value -5 away from 0? And we would measure that sort of thing. Now, you might notice something about this. Giving this sort of attribution to the single number -5 does kind of feel like we are giving it a distance, a geodesic, if you would, in terms of we are measuring in particular the distance away from 0 whenever we measure this value of absolute value of -5. And indeed, that's exactly where we're saying that normed vector spaces are special examples of metric spaces, because what we're adding on to it is an attribution to each number that satisfies a certain number of properties, one of which is going to be a triangle inequality. And once we go through and see this and kind of put everything together, we are going to get to see normed vector spaces as a special class of metric spaces as well. So these are metric spaces with kind of 2 extra layers of kind of building together the structure of these objects that we're looking at. Well, not only do we add in a norm rather than a metric, which is something that generates a metric, but that a metric could not generate a norm. So this is something particularly stronger here, but we're also adding in the addition and scalar multiplication algebraic operations of a vector space, something that we learned about and worked with in linear algebra. So we'll talk about in this particular week of talking through today about how we can extend what we've done with linear algebra to incorporate this essence of a norm. Now, I want to go ahead and mention that it may be a good idea to go ahead and start taking a look back at some of the things that you've talked about in linear algebra courses in the past, whether that be computational linear algebra or whether it be just your undergraduate linear algebra course. Either one of those is going to have the terms that we need. We don't need all of the computational heavy stuff. That's not what we're trying to build upon in this class. Only the things that the level of undergraduate, in particular, I'll go through a list of some terms that are going to be good for us to know and have access to in the future here. Because we are going to be building upon this structure of linear algebra to get a notion of lines in our space. Linear algebra, well known for dealing with lines. We talk about notions of something called a linear function, which is something that we'll be talking about next week in some spaces in which we aren't thinking of linear transformations as just matrices. They could be something more. We'll discuss something called an operator on a linear space or a vector space, and we'll get into that sort of discussion next week. But the only way that you can make those sorts of operations is if you're able to draw lines in your space. Essentially, vector spaces allow us to say, not only could you just draw a vector, right, but you could do 2 times that vector. And the space of all scalar multiples times a vector can be considered a line, right? All things of that form can be considered a line in our space. So drawing lines in terms of Rn or Cn, or even though this is harder to imagine, the space of all polynomials. Say, for example, P sub n, which is the space of polynomials of degree less than or equal to n. You might consider this sort of space and think, how do I draw lines in this space? The idea is that a line going through a particular polynomial can be multiplied times just any real number, where here This is an element inside of the polynomials, and k is just some sort of scalar multiple. Considering the space of all of this, case of kp, where k is just a real number, this gives us a line in this space of p sub n. Now, it's interesting because you can now think, okay, well, if that's what lines look like, can I imagine a structure that looks a little bit like p sub n? And in linear algebra, we say, yes, you can imagine this space p sub 1 or p sub n as being the same thing as r to the n plus 1. Essentially, that there's the same number of dimensions in the two spaces in terms of the polynomials of degree less than or equal to n and r to the n plus 1. The idea of what is making it so that these two things look very much the same. Let's say, for example, we're looking at P2. So we're looking at polynomials that are of degree less than or equal to 2. Then what you can do is you can imagine the thing you're doing is taking a polynomial that has a degree less than or equal to 2. So even if a sub 2 is 0, this is still going to have degree less than or equal to 2. So you can imagine that this value, this polynomial right here, is getting mapped to the R3 vector, which is just the coefficients of this polynomial inside of R3. And there's a way to think of these two things as essentially algebraically having the same structure, this polynomial over here on the left and this R3 vector over here on the right. Indeed, we can eventually end up utilizing some sort of argument that says that all finite dimensional vector spaces really just look like some sort of r to the n. All right, so they have some sort of structure that makes them look like this. So the idea is that all of these kind of have this sort of linear sort of format. We want to be able to draw lines in our space. And so visually speaking, that's the difference between what we do when we consider vector spaces rather than looking at metric spaces, in which case we can only form perhaps a geodesic between some 2 points. It's hard to know what happens outside of those 2 points. At least the metric does not give us that sort of understanding because there's no way to multiply a point times 2 in a metric space, for example. Here are those axioms of a vector space. So axioms for a vector space V. These are labeled based on what we did in our 632 class. Maybe you've seen these axioms before in 632, which was previously called 689. So our intro to graduate level mathematics course. So working with these types of axioms in this way, you can see that they share many of the properties that we talked about at the very beginning, on top of a couple of other things that essentially just tell us, oh, they work the way that we hope that it would. That if you try to scalar multiply times an addition of two vectors, then the scalar could be distributed. And the same thing works with the vector on the outside of the parentheses. You also get commutativity and associativity. You also get additive inverses for these vectors, that these all exist. Essentially, these properties together are what guarantee us this notion of lines working the way that we want it to. Essentially, it is concretizing our geometric intuition into algebraic form. There are a few words to kind of keep in mind here as well, which is that you could be looking at this all in terms of the space Cm instead of Rm. That is, you could be looking at all of these scalars inside of your coordinates to be all going to be forms of coordinates of the form a sub I plus b sub I times the imaginary value, square root of -1, which we'll write as I. And hence I'll use a different letter when I'm trying to do an index of these numbers here. But you can imagine that this becomes like a sub n plus b sub ni as you go throughout here. So these are the coordinates of something that looks like it's inside of Cn rather than in terms of Rn. But you might remember, or maybe this is a new thing for us, this sort of vector space, at least in terms of how it looks as a vector space, algebraically speaking, can be written just in terms of r to the 2m. Because you can think that each of these scalar values here, a1, b1, each of these is really just a real number. So really thinking about the complex numbers as R2 should not be that far away from us. Even with this picture, this kind of helps, right? You have this sort of notion of a real and an imaginary axis to be graphing your complex numbers. Like say, for example, if something is 3 to the right on the real axis and 4 up on the imaginary axis, then you have the number 3 plus 4i. So there's really a picture-wise connection here between complex numbers and the real numbers squared. This symbol that I'm using right here is that of something called an isomorphism. The isomorphism can mean just has the same structure as. And in particular, we're saying that they have the same algebraic structure. That means that they have the same notion of addition and scalar multiplication. In particular, you might see me add sometimes that these two things are equivalent as vector spaces, because I cannot go any farther in terms of the structure that they have in order to keep that same sort of isomorphism. They have the same algebraic structure as two vector spaces. Their addition and scalar multiplication works very much the same way in terms of the picture that we have here on the right. Now, the spaces of Cm or Rm, whichever one that we're working with, these both are finite dimensional spaces, which means that there exists a finite set of vectors so that every vector can be written as a linear combination of those groups of vectors. I suppose here I should have put M, so let me do that. Put M right here. The standard basis for Cm is just going to be all of those vectors that are of the form 1 in one spot and zeros in the other spots, the standard basis for each of these things. So this is going to be a way to write any vector here in Cm in this particular form. Then if we're given a vector inside of Cm, then we can write any vector x1 to xm as a linear combination of those standard basis vectors. In fact, this is true for any basis. So you could write this as a linear combination of these x sub I, e sub I. Since the x vector is arbitrary, we see that the vectors e sub j span c to the m, which means that any vector inside of our space can be written as a linear combination of the basis vectors. Then finally, since the vectors are linearly independent, which means that whenever you take the sum of this linear combination format and set it equal to the zero vector, that there's only one way to get to the zero vector, by adding scalar multiples of these basis vectors together, and that's when all of the scalars are equal to zero. Then adding together the notions of span and linear independence gives us something called a basis for our space, and we say that C to the M has dimension. A quick thing to note here, you might have noticed something interesting here, that the basis elements that I was given right here were of the form ones in this spot and zeros elsewhere. But you might ask a question, okay, well then how am I supposed to think about this with the complex numbers here? So for example, we might look at the example of C2, right? And you might ask, how am I supposed to take this basis and get a vector of the form 1 comma I? At least in terms of the standard basis elements that I seem to be writing over here. So here's our example. How would I write the vector 1 comma I as a linear combination of the standard basis vectors of 1, 0, and 0, 1 that this example is giving us? Well, the interesting thing about this is that there's one thing that I have glossed over here that does end up becoming a little bit important here, which is asking what type of vector space it is that we're looking at. So this is something that is going to play a little bit more of a role here in terms of visualizing these sorts of spaces, which is that vector spaces could be either real or complex. Whenever we think of C to the N, we're typically thinking of it as a complex vector space. This is a complex vector space. And what we mean by that is that the bases that we are using here, the scalar multiples that we're allowed to use in forming linear combinations, they are allowed to be imaginary. So they are allowed to have a complex, non-zero complex component to those scalars. So for example, I could write the vector 1i as 1 times the vector 1, 0 plus I times the vector 0, 1. On the other hand, the vector space R2, these vectors I can only work with in terms of real scalars, because this is something I consider as a real vector space. Meaning that the scalars that I use here are limited to only have complex component of 0. So in order to get a vector of the form 1 comma 5, the only thing that I'm allowed to use here are real numbers in terms of my scalars. So you can see here the difference in between writing something like a vector 1 comma I in C2 and something like 1 comma 5 in R2. The difference is that these are allowed to be any complex number whenever we're considering a complex vector space. In this way, now I don't have to make another vector that says, okay, here's 1 comma 0, and here's another one times, but that's just I times I comma 0. I am not needing to write another vector here in order to make another basis element. But you might have noticed that I made a little interesting distinction here, which is a fact that as a real vector space, the complex numbers has dimension 2. The complex numbers has dimension 2 as a real vector space. So considering complex numbers like c squared, typically whenever I'm not going to be specifying anything, I'll think of it as a complex vector space, as that type of structure typically fits. When we're thinking of complex numbers, we would like our scalars to be complex as well. In which case, the complex numbers C2, this one actually is the one that has dimension 2 as a complex vector space. But notice that the complex numbers as a real vector space itself has dimension of 2. So you can imagine in this case, and indeed it is true, that C2 is then 4-dimensional as a real vector space. Now, what's making the difference between these two dimensions? Remember that dimension is determined by the size of the basis. The basis of the complex numbers as a real vector space, can you think of what the two values are? What are the two complex numbers that would become a basis for this as a real vector space? And remember, again, the distinction real vector space means you only get to use real scalar multiple values whenever you're forming linear combinations in that space. Indeed, it is going to be 1 and I. 1 and I is a basis as a real vector space, because any value in terms of the complex numbers can be written of the form a plus bi, which is a times 1 plus b times I. Here, a and b are only allowed to be real numbers when I'm considering this as a real vector space. And indeed, any complex number can be written to be of this form where a and b are real numbers. So because of that, the complex numbers has dimension 2 as a real vector space. Now, typically, we will be using the fact that this is a complex vector space, and we'll kind of make that assumption as we move along. But that does give us an interesting kind of connection here between the complex and the real numbers. Typically, when we go through these classes the first time, we're only working in real vector spaces, but complex vector spaces are just as useful, if not more useful, coming up to this level of mathematics. So whenever you see C2, I'll go ahead and imagine that we're looking at this as a complex vector space so that its dimension is 2. But sometimes I might make a distinction C2 as a real vector space, in which case this would be a 4-dimensional vector space as a real vector space. Here are some examples of some of these vector spaces that we've looked at already in previous courses, things like Cn, C infinity, the space of sequences. Notice that it's possible to add sequences as well as scalar multiply by adding coordinate-wise, as well as scalar multiplying each of the coordinates in that sequence. We also get a trivial vector space, which is just the vector 0. We also have the space of n by n matrices. This is itself a vector space, and you can imagine what lines look like here in this side of the space. It's very difficult to think about how many lines there are in spaces of all functions, like f of k. Here, k is going to be a field. Whenever I write k like this is going to be a field. Typically, the fields that we're looking at are going to be either the real numbers or the complex numbers. However, you may be familiar with other fields, and you might think, can I go through and write those fields in there? And the answer is yes, you absolutely can. So the space of all functions from either the reals to the reals or complex to complex, this is itself a vector space with addition and scalar multiplication. There's a notion of a 0 vector in here as well, which is just the 0 function. You can also clarify this and put down the space of all continuous functions. If you put a space on your field or a particular structure on your field that allows it to have this notion of continuous, that is open and closed sets, if it has some sort of topology on it, perhaps a metric on it, in which case the real numbers and the complex numbers do, then you can think of the space of continuous functions as a vector space. And again, this would work for even fields beyond the real numbers and the complex numbers, as long as your field is a topological field, right? So K has to have a topology on it. We've discussed that sort of topology is a notion of having open and closed sets. The only reason we need that topology is so that we can define continuous in the right way, right? We can define a continuous function in the sense of if there is an open set in the codomain, then it maps backward. The inverse image of that open set is also open in the domain. Then we have the space C1R, which is the space of all differentiable functions going from the reals to the reals, whose derivatives are also continuous, and we could call those continuously differentiable functions. If you could take infinitely many derivatives of a function, then you get a smooth function, and that is also a space, which is a vector space. And finally, you've got the space of all polynomials, not just the ones of polynomials of degree less than or equals to n, of which I've been calling them p sub n, but you could also take the space of all possible polynomials. We here, n is allowed to just be any real number, or rather any natural number, to kind of cap off how many values there are here. We've also talked about in the past a vector space being having vector spaces contained within it oftentimes. A vector space is a subspace of itself, but a proper subspace is going to be a proper subset of it that also has all of the properties of a vector space whenever it gets the same algebraic operations from its larger vector space kind of supergroup of it. So the subspace of V is something, a subspace of V is something that is a vector space in its own right. That's also closed under the notions of vector addition and scalar multiplication that it gets from its parent space. For example, you could consider the space of all polynomials. Since these polynomials are infinitely differentiable, this would be a subspace. I can add and scalar multiply as inside of a subspace. It's got 0 in it. So all of those three things put together tell me that I could get a subspace of something that is contained within. So I know that's first that P of R is a subset of the smooth functions and is non-empty and is closed under the algebraic operations. And has all of these things together give us something that is a subspace of the vector space. Now we've finished where we're talking about the algebraic operations. This might have been a review for you, or maybe there was a couple of spicy things in there. I hope that there were. But it's nice now to think about, okay, what else do we consider on this structure that sometimes we just automatically start using without thinking about it? And the extra structure that we're going to be looking at here is that of a norm on our space. So we're going to add on one extra layer here, which is that of a norm on our space. A norm is a way to think of I want to go beyond just saying a distance from 0. I want to go beyond that and just say that it is something that works neatly and continuously throughout our space. It is a scalar value that you could attribute to any particular vector here that tells you a little bit about that vector. It tells you something that's, I've been using the terms length and size, but I want to go ahead and kind of think a little bit beyond that, because metrics here kind of also say, okay, well, here's the geodesic. I can consider maybe how far these things are from each other, but I can't consider how far they are from a particular fixed point. Only thing that I know is that they fix triangle inequalities between any triangle points. The notion of length is not something that is set in stone for a metric space. I can't go through and tell you, okay, this is what this point is by itself. I have to always tell you what that point is in relation to all of the points that may surround it. I cannot give you any information about the point itself without relating it first to another point. In a metric space, that is absolutely the case. Metric space cannot get information about a point without referring to another point. Whereas that is absolutely possible here with this notion of length and size for the norm space. I can plug in a vector inside of a vector of a norm space, and I can give you a scalar value that tells me something about that. And one way to think of it is that it is kind of the length or size of that vector space. A way to think of that back in terms of distance is to think how far is it away from zero, because as we'll see, the norm, the zero vector is going to be the only vector that is allowed to have zero as a norm for that vector. Everything else has to have some sort of non-zero norm to it. So it's asking about how far away we are from zero in terms of that. In fact, you can see here for our norms on Rm and Cm here, that these norms define metrics. D of x comma y, defining it as the difference in norm, the norm of the difference between two vectors, x and y, gives you something that is a standard metric on the space of R or C. So norms can help us define metrics. At least we see that in this particular example, and we'll see that in full later on, that you can take a norm and generate a metric onto your space. Now notice that there are definitely ways for that not to occur. For example, in our homework, we will discuss the example of the discrete metric. So example, the discrete metric on a space X cannot be, and we'll use the term induced here to mean that it comes from, it cannot be induced from a norm on that space. So the discrete metric is special in that way. It is something that is a pure metric. It cannot be induced from something that comes from a stronger amount of structure. It cannot be induced from a norm. We'll talk a little bit about that as we go through our homework as to how we can actually determine that, say that it does come from a norm. What things can you conclude from that? And you can try to break perhaps one of these three qualities about something being a norm. Those three qualities being a norm has to have these three things. One is that it has to be greater than or equal to zero for any vector that you plug in it. With equality, meaning it's only equal to zero whenever you're looking at the vector zero and plugging that one in. You can also notice that some of the things about norm work neatly with lines. If you take a vector and you multiply it times a specific scalar, then its length should change also by that amount. Now, I do have to put absolute values whenever I take it outside of the norm symbol, and that's because lengths have to be greater than or equal to zero. But you can think, for example, if I take a vector and if I multiply it times 5, then I need to be able to say that the length of 5 times u is equal to 5 times the original length that I was working on it with. That is, the ratio between the two lengths of the vector should be 5. If I scale a vector times 5, the length should be scaling times 5. That same thing should be true if I plug in -5, because if I'm measuring lengths, putting a negative out front should give me the same length, but only change the direction of that value. Since I'm measuring length, that's just going to be 5 times the vector u. And then finally, we need the triangle inequality as well, which is that the norm of u plus v needs to be less than or equal to the norm of u plus the norm of v. These things all put together give us what is called a normed vector space in a particular vector space V. So let's go ahead and see another example of this in terms of our functional vector spaces that we've been looking at. There's a notion of length for functions. Let's take the functions that are bounded going from a space X to a complex number C here. Then let's go through and say that this value here, the norm of a function f, is going to be the supremum of all possible values, the absolute value of that function f of x. Here, actually, it's not an absolute value. Since we're going into the complex numbers, we will often refer to this as the modulus of f of x. This is typical in terms of complex analysts. They will say, okay, well, the absolute value of a complex number, that seems to signify what? Right? Like you get some sort of number that tells you its distance from zero, which is exactly what we're saying. But typically absolute value is used in the contexts of real numbers. And so when talking about things in complex numbers, you typically hear the term modulus. So think absolute value in R is the same idea as modulus of a number in the complex numbers. So for example, if you plugged in a value to a function and you got 3 plus 4i, then what this set inside of here would actually be a set of real numbers, which are the moduli of this number. The absolute value of 3 plus 4i, square root of 3 squared plus 4 squared gives us 5, the modulus of this imaginary number inside of the complex numbers. So because the function f is a bounded function, we know that this supremum should be finite, which allows us to define this as a supremum norm for the uniform norm. And then indeed defining the distance between two functions to be the norm of the difference between those two functions, then in fact, what you get out of that is not just a metric on the set of bounded functions, but you might recognize this as the uniform metric. That is the one in which things converge uniformly whenever they converge in this metric. So you get a little bit of connection there. That is that many of the things that we talk about in terms of metric spaces all carry over to these spaces that have norms on them, as long as we know, okay, here's the kind of stuff that we know from metric spaces, all of them get copy pasted here for normed spaces as well. And what's more, because we have this extra layer of structure of that of a norm, we might be even able to even say even more about our spaces. And we'll see a couple of things that we can do with them this week as we go through it. But just so that you recall, we're not actually leaving everything behind from our previous weeks. We're going to be using all of that stuff in what is to come because our norm spaces are metric spaces. So they have the same properties and the same theorems wherever they're appropriate to use. So we've seen some examples of these norm spaces, looking at Rn and Cn and defining norms on each of these. We've seen an example of normed functional vector spaces as well, and we've seen how we can define a norm on any space. After getting that norm, this proposition tells us that we actually can now measure a metric on those spaces in the same way that we did for the others. And I would encourage you to go through and walk through this step by step. I believe our reading is going to have an actual step-by-step proof of this. But the main things here, the main points of this is making sure that it satisfies 1, 2, and 3. And I think that it might be a good challenge, even if you haven't had the chance to read through it yet, to try this yourself. Can you say that this is always going to be a metric in the sense that it satisfies the 3 conditions of a metric that we were given from before, given that it satisfies these 3 conditions here? Instead, let's go through and see some of the properties of norms once we have them. It turns out that these 4 things come directly from the definition of a norm, and we don't even need anything extra to talk about them. Any norm space has an induced metric, so our notions of convergence, continuity, completeness, compactness, point set topology, all of these sorts of concepts are all going to carry over for us into this new section. The only difference is instead of using the notation for distance between u and v, using this kind of little d variable or perhaps a rho, depending on what the context is, then we will use the norm of the difference, u minus v, and talk about that as the distance between 2 vectors in a norm space. So, for example, you'll see that whenever the sequence x of n converges to x inside of this norm vector space, then the way that we write that is the distance between x and xn goes towards 0, and this is how we're writing that distance. The condition 2 is the inverse triangle inequality, and the same proof techniques that you used to do this inverse triangle inequality back in week 2 homework still work neatly here. For vectors u and v, you have this property of the absolute value of the difference between 2 norms is less than or equal to the norm of u minus v. Notice that all of the ideas here are kind of the symbols here. They do refer to what you want them to. This single absolute value bar on the left and on the right here is appropriate because the values of the norm of u and the norm of v, these are real numbers. You can never have a norm be a complex number. So these are real numbers here. So the difference between these, and you have an absolute value outside of them, that all is notation appropriate, and hopefully helps signify to you as well, if you get confused, that if you plug a vector into a norm, then what you're getting out is a real number. So for example, this convergence that's going on right here is a convergence of real numbers going towards 0. It's not convergence, say, of metric space values. It's actual real numbers. So you get to use that sort of structure that you expect from the real numbers there in working with those things. Then the function of the double bar, which is the function that sends a element of a vector space X and gives it the norm of that vector. This function here is a continuous function. Basically, we can think about what that would mean, right? It should mean that if you have a sequence of elements, x of n, that converges to x, then that needs to imply that the norm of x of n converges to the norm of x. So when I gave that rather kind of vague description of how I think of the norm as like a continuous variation, what I mean is that there's a way to think of these vectors. If they converge to another point continuously inside of a space, then so do their norms. So then they also converge in norm. So this is essentially what's going on. By the way, this condition 3 follows directly from the condition right above it, because if x of n converges to x, then utilizing the fact that we need to know that x of n converges to x, this is the value that we want to show goes towards 0. But this is bounded above by the very norm between x of n and x itself, which we know goes towards 0. So the norm values, the y values of this norm function, are going to go towards 0. And the last thing too, which is something neat and that we've seen kind of before when looking at functions and functional vector spaces, is that if you have vectors x of n that converge to x inside of a vector space, and then some scalars alphas of n that converge to alpha, that is in terms of scalar values, so that's a scalar convergence, and this is a norm space convergence here, then alphas of n x of n converges to alpha x. The proof idea that you maybe have seen before already in this class is that you can break this up utilizing the triangle inequality into two separate norms that you need to show go towards 0. Maybe we can utilize for both of these the notion of, well, there's a scalar to take out here. And maybe over here, there's a scalar to take out. So using property 2 of norms that allows you to take out a scalar. If you go through and utilize this extra lemma that you'll need to throw in there, showing that if the sequence x of n converges, that the sequence of the norms of x of n is bounded, then you should be able to go through and complete this proof for number 4. And I recommend that you go through and try out the steps of figuring out how that sort of thing looks. All of these propositions automatically come from just looking at what we've done with metric spaces and borrowing them pretty much from how they look inside of this world. In particular, 3 and 4 end up being a little bit newer to us, that we can actually use norms as continuous functions, taking us from a vector space to the real numbers. So some neat stuff going on here. Here's some more examples. We've had a few of these already in looking at what these things are. So, but we haven't actually talked a lot about them. You may remember in an optional video from week 3 that we talked a little bit about this norm between for a vector in little LP, and said this is something that works neatly with our space. And here is that space right here, the norm of the vector x equaling the sum of the p of the values of this sequence, all raised to the pth power, and then that entire sum being taken to the pth root. So this is a norm space with a norm given by this. In fact, the proof of this essentially follows from many of the same techniques that we used back in that week 3 optional video. And in fact, the induced metric is the one that we defined before. So looking at spaces like little l1 and little l2, these two spaces each are norm spaces on top of just metric spaces. Recall that these spaces, by the way, were, if you take a little l1, then you're looking at the absolute values of your space and saying that the sum, the absolute values of these are finite. And then for L2, you're saying that the sum of these values squared is going to be finite as well. So little L1 and little L2 each have their collections of sequences with them, and we'll see a little bit more and start experimenting with these some more now that we know that these things have norms on them as well that are well defined. So this is something that you may have seen has a lot of oomph behind it. The theorems back in week 3, which I encourage you, if you got a chance to look at them before, go back and look at them again. Those theorems talk about these sorts of norms, and they talk about how complicated it is to figure out that these things have the norms that we're hoping that they have. We needed things like the Helder inequality to get to that point, which I'll mention briefly in kind of the proof of some other sort of future theorem that we go through here. But some of these examples and showing that these things satisfy things like the triangle inequality are very tricky. But nevertheless, spaces like these are very useful for us. Little LP in particular, and these big LP spaces that we have in this underneath example, for instead of looking at sequences, looking at functions and integrating rather than summing, then these vectors from closed intervals a comma b to complex numbers, these values here for the norms of these functions are also norms on this space of continuous functions. Notice in particular that this tells us something about the space of continuous functions. The continuous functions on a to b, whose functions are bounded, and we know this because we are taking continuous functions on a compact set, and so those functions are also going to be bounded. This has 3 different norms. And we could call them either the one norm, which we have the definition of which is right up here. We have the 2 norm, and then we also have the norm, which is the one that we defined up near the very beginning of this, that the supremum for all x inside of AB of the absolute value of these moduli of f of x. This particular last norm is sometimes called the infinity norm, this value right here. And we might recall that we used some of this terminology with D1, D2, and D infinity. So we could use this same nomenclature in talking about norms too, these subscripts of 1, 2, and infinity for each of these norms. So just like how the space of continuous functions had a bunch of different metrics on it, in fact, it has several different metrics that come from norms. D1, D2, D infinity all come from these norms of F1, F2, and F infinity. There's one more space that I want to give a norm to, because we haven't talked about matrices in a long time. In particular, for this one, we are going to want to go back and remember some things from linear algebra in our linear algebra. In our next section here for this, in this video, I'll talk a little bit more about how this sort of operator norm is gotten. And it's going to utilize something called the principal axes theorem that I discussed in my 632 class, and I believe is also discussed in intro to grad level mathematics courses through this program. So if you would like to take a look at that, it is in the text of Ricardo, for those of us who have taken 632. Otherwise, you may have something in your textbook that allows you to say, okay, why is it that symmetric matrices are orthogonally diagonalizable? So those are the words that you're looking for there. If you want to maybe try and find that in your book, if you can get up to reading to that point, then you can start understanding where this sort of proof comes from for this final example, which is the space of m by n matrices. This space has an operator norm on it. We'll define the operator norm in this way. Given a m by n matrix A, we're going to define it based off of the values of the norm AX. Now, here, this norm of AX, I'm going to be utilizing a particular norm for the space, and usually the one that we end up using is the 2 norm on that space. AX is a vector inside of Cn. So we're using that 2 norm in Cn whenever we consider this norm right here. So notice that this is the norm that I'm defining as the operator norm. So perhaps I could go through and give a different name for it. Maybe I could say that this norm A has a subscript of m for working with the set of all matrices. Then we could go over here and say that this norm over here is the norm of sub 2, to say that this is a norm that we are defining over here. There's a couple dots right over on this side. And then on the right-hand side, we have a norm that's already defined, and we're taking the norm of A times the vector X. Here, the vector X is something that you could plug in to the linear transformation for which the matrix is A, and you can get out a Cn vector from multiplying through those things together. Actually, I suppose that this should be a Cm vector, shouldn't it? Because if you multiply through this, you should get out a Cm vector. So these should be m's throughout. So here we go. At least with regards to how the matrices are ordered here, should be a Cm vector to get out of that. Then what vectors x are we going to plug in to find this 2 norm? In fact, we're going to be plugging in every single vector x that has a 2 norm equal to 1. If its 2 norm is equal to 1, that is, if everything inside of this ball is mapped through, then we're going to basically ask, what does the matrix A do to the unit ball? You may remember, because I showed this in a video lecture in 632, for those of you who've had it, that there is actually a way to go through and see what that unit ball looks like and how that kind of maps through. I'll pull up that Desmos here just real quick. So here is an example of what this might look like. So here I have taken a matrix which is 3, -1, -1, 3. Let's take this circle here, which is the unit circle inside of R2. And let's see what happens to the vectors of this circle if I go through and take them all and multiply them times the matrix A. Now, there's a process to go through and do that. We do a little bit of a change of variables to try and figure that out. And essentially what we end up getting from that is this black oval, this ellipse out here on the outside from multiplying through times this matrix, 3, -1, -1, and 3. For example, if I went through and I mapped in the vector square root of 2 over 2, comma, square root of 2 over 2, which is a vector on the unit circle. And if I plugged it in through this matrix, then you could go through and calculate that what I end up getting is this point right up here. This is just square root of 2, comma, square root of 2. This multiplied that vector times 2 whenever I went through and multiplied that. You might remember that that means that this is an eigenvector of this particular matrix, which is going to be useful in how we classify this sort of notion of norm. But to find the norm of this, we're going to be taking all possible values of what happens when you plug in a vector on this unit circle and get out something in terms of its range from that matrix. And we're going to be looking for the vector of the largest 2 norm length. We're going to be looking for the thing that stretched the most from this. And you might notice that the vector that stretches the most is going to be at kind of the major axis end of this ellipse. And I've got a little blue line going right through it. That blue line is coming through because actually it turns out, and this can be calculated, that this blue line corresponds to an eigenvalue of the original matrix A. That is, -1, 1 is an eigenvalue of this matrix, 3, -1, -1, 3. And it actually is going to get multiplied times 4. So you can imagine kind of how we might utilize eigenvalues here. And indeed, in our proof that's going to be coming, we're going to see that this notion of an operator norm comes directly from finding the eigenvalues of a particular matrix. So in particular, the norm of this matrix, 3, -1, -1, 3 here, is going to be 4. The norm of this matrix is going to be 4 because it is the largest possible scale up that this operator takes for anything that is of norm 1 on this green circle here. The largest possible scale up that it does is a scale by a factor of 4, which is here on this eigenvector. So let's take a look at what the eigenvalue is going to be. Now, you might be surprised because you might think, okay, well, it's just going to be the largest eigenvalue of the matrix A. But there's a little bit of a distinction here, which says that this needs to be the square root of the largest magnitude is the eigenvalue of largest magnitude of the matrix A transpose times A. In particular, the largest magnitude here that I mean is that you need to sometimes take a negative eigenvalue in order to make this work. Think about why I might, for example, with a matrix with eigenvalues 1 and -3, why I might want the eigenvalue of -3 first, which is that it's going to flip over the vector that I plug it in, but then it's going to make its length multiply times a factor of 3. In terms of the norm, it doesn't really care about whether or not you're flipping over the value, so we need to pick the one of the largest magnitude or of the largest norm. So what we do is we end up comparing the norms of this one, and we pick this, the -3 here because it has the largest possible magnitude. I've gone back and changed the wording of that to make that a little bit more clear. So that's one thing that makes it interesting. The second thing is we're not looking at the matrix A here. We're looking at the matrix A transpose A. Why aren't we just looking at the matrix A to begin with? Because can't we just go through and find eigenvalues and eigenvectors of the matrix A and then find the largest one of those? And some of you know the answer to this. The answer is no. Not all matrices have even one eigenvalue. The matrix 0, -1, 1, and 0 is a rotation matrix. It rotates a vector 90 degrees around and has no eigenvalues and no eigenvectors. So what do I need to do with this? Why A transpose A? What happens here? What ends up here is that I get something called a symmetric matrix. And symmetric matrices always have plenty of eigenvalues and eigenvectors. And that's going to allow us to apply this principal axis theorem and what is to come. Before we get into that proof, here is a calculation for how we might find the norm of the matrix given this information. To find the norm of a matrix like 1, 3, 0, 1, first thing I'm going to do is calculate A transpose times A, and I'll get what? 1, 3, 0, 1 times 1, 3, 0, 1. You might notice that this is itself a symmetric. Oh, no, it's not. I had to switch the order here. So 1, 0, 3, 1. And then times the matrix 1, 3, 0, 1. And if I go through and multiply these together, then I should get a symmetric matrix. 1, 3, what is it? 3, and then 10. Something like this. This is a symmetric matrix because its transpose is equal to itself. I'll use a different letter. Its transpose is equal to itself. Switching the rows and the columns gives us the same matrix back. Because this is a symmetric matrix, I should have plenty of luck in trying to find eigenvalues and eigenvectors. So why don't I go through and take that process? I'll need to take the determinant of A transpose A minus lambda times the identity matrix and get the determinant of the matrix 1 minus lambda, 3, 3, and 10 minus lambda, and set that determinant equal to 0. And let's see what I end up getting here. Should get something like lambda squared minus 11 lambda, and then what? 10, 9, so plus 1, something like this, and setting this equal to 0. So the values of lambda that I'm going to get here are going to be going through and applying the quadratic formula, 11 plus or minus the square root of 121 minus 4 times 1 times 1. So this is 117 divided by 2. And those are the eigenvalues of A transpose A. Now, from that point, I need to go through and find which one has the largest magnitude. And since lambda max is going to be the one with the plus inside of it, as the minus is going to make it a rather small number in magnitude, I need to be choosing this one with the plus inside. Then the value of the norm of the matrix A, is going to be equal to the square root of 11 plus the square root of 117 divided by 2, utilizing this operator norm. So this is telling us at the largest possible vector, how much is this matrix A scaling a vector? How much is it scaling the vector? Now you might ask, why didn't we just go through and do the eigenvalue thing again for this particular matrix? And there was one answer that was given at the beginning, which was that oftentimes we don't have enough eigenvalues and eigenvectors to work with. Sometimes we don't even have any to work with to get the full amount of information as to what the norm of a matrix should be in that scenario. And the second is that the largest possible value of scaling in being the eigenvalues and eigenvectors, that picture is only good for symmetric matrices, at least in general. So having that notion of how that works for eigenvalues and eigenvectors, that picture that I showed from Desmos works for symmetric matrices. But it turns out that if we work with A transpose A rather than the matrix A, then we're pretty much good to go because we have our eigenvalues and eigenvectors and our picture works the same way. But that's going to beg the question a little bit. Why is it that that picture works? And so let's go ahead and take a look here for how the principal axis theorem starts coming into play. But that begs the question a little bit. What is it about this picture that allows us to say that the place where you have eigenvalues and eigenvectors is the thing that gives you the norm, the largest possible stretch of a matrix times a vector from the unit circle? And that's something that we'll be talking about later on. We'll want to talk about something called inner products next week before we get into that sort of discussion. And we'll use that to wrap up our notion of these finite dimensional operators, which we'll go through and define and discuss in the future. But this operator norm is something that is the beginning of something that we'll talk a ton about in section 5.4. We're going to generalize this notion of operator norm into any sorts of linear transformations that take us from one space to another. And we'll talk about that once we get closer to that spot. But for now, we can go ahead and clarify what this notion of norm is. So that will do it for me today. We've gone through and talked a little bit about what norm vector spaces look like. What is their geometry? How do we decide? How do we define and work through sort of some of the algebra of it, as well as understanding this analytical object, looking at the norm as a sort of way to gauge the length or the size of a vector inside of our space. We've gone through a ton of examples here that we will be building upon here for the future. But that'll do it for me today. Thank you so much. Have a wonderful day.